Excellent. So hello and welcome to my demonstration of the April APL compiler. April is a project that I began in 2017, creating a compiler that changes Common Lisp into APL. So when we think of APL, we typically think of it as an interpreted language, but APL compilers have been built since the 1970s, and April is another iteration of in this category. So April is, in this talk, I'll be discussing some of my design philosophies behind April, process of developing it, and some of its real-world applications. And one of these applications you can see right here. This device emitting the colored light is called Bloxl, as Rich was just mentioning. This is the product of a hardware startup I'm working with, and it uses Common Lisp and APL to drive these graphical patterns. But we'll get to that later. So first off, some history. Many people think of APL and Lisp as very different languages, but they have some surprising parallels in their evolution. Both of these languages originated as a mathematical notation. Lisp was created by John McCarthy, who was a computer scientist and a math professor, and his goal was to create a notation to express the lambda calculus. He, like Ken Iverson, he didn't originally anticipate that his notation could be evaluated using a computer. But one of his students, Steve Russell, wrote the first Lisp interpreter for the IBM 704 mainframe. And McCarthy was quite startled, but he took this in stride and immediately joined in on the development of Lisp as a computer language. So Lisp was the first interpreter was built in 1958, and it was first compiled in 1962. And since that time, Lisp has been seen as a compiled language. So McCarthy and Iverson were both originating their notation ideas in the late 1950s, but Lisp was implemented on computers sooner than APL was. And it's notable that both Lisp and APL were simplified from their original concepts for use on a computer, just as the Lisp notation lost its the APL notation lost its superscripts and subscripts for use on a teletype. Lisp shifted from using what are called M expressions to S expressions. That is a set of parentheses with both the function name and the set of arguments all inside them. So while Lisp is seen as a compiled language, Lisp doesn't have the kind of interactivity process that you might expect. Most people think that a compiled language means you just write static files of code, run a compiler, test your output, and then recompile. But like the vector languages, Lisp uses rich REPL interactivity and has been known for this for a long time. It's also notable that Lisp and APL both rose to prominence during the mainframe era, and they started to fall out of favor when the microcomputers took off. Because they're both garbage collected languages, the early microcomputers didn't have enough horsepower to run them as much more than toys. So this was a hurdle faced by both of these languages. It is notable, though, that APL powered one of the first microcomputers, that MCM70, but it didn't get very far. And Lisp is also notable for having powered a series of Lisp machines. These were computers that were optimized to run Lisp on the hardware level. And I guess you could say the MCM70 was an APL machine, but the Lisp machines evolved considerably more. There were two companies called Symbolics and LMI that released Lisp microcomputers, which were some of the most unique computing machines ever developed. But enough history for now. Let's take a look at a modern Common Lisp environment. So let me know if you can see the Emacs interface here. This is the REPL for Common Lisp. So this is Emacs. It's an editor that anyone who's used Unix family operating systems has probably seen at least once or twice. And it's the tool of choice for Lisp developers. Emacs is built on a dialect of Lisp, Emacs Lisp, but it's also used to interact with just about every other flavor of Lisp. So I'm using Common Lisp, and in particular, Steel Bank Common Lisp, or SBCL. Common Lisp was created when several different Lisp vendors joined together and decided to basically unite all the best features of the different commercial Lisps out there into a standardized implementation that could be implemented in different ways. So all the common Lisps have a core functionality in common, but they have different strengths. Like SBCL, for example, is known for fast compile time and fast execution time. Others are strong in different ways, like there's ABCL, which is compiled on the JVM and embeddable Common Lisp. But let's start with some Lisp syntax. So the S expression here, we're going to add 1 and 2. So that's the addition function. Multiply 2 and 3.
Don't think we can quite see. Oh, there it is. There was a bit of a delay there, yeah.
Yeah.
We can see it now.
Okay. And then I just wrote a function. This is the add 3 function. It simply adds 3 to its argument. Add 3 to 5, and I get 8. So one of the notable features of Lisp is considered a language with strong metaprogramming, the ability to write code that generates other code. So we'll do a very simple analysis, a very simple example of this now. So as I was saying, Lisp features macros, which can be used they are code that generates other code. So I'm writing a very simple example right now. So we try our +2, 3. Now let's feed the +2, 3 to this macro. So here we get 2 minus 3. 2 plus 3 is changed to 2 minus 3. So what this macro does is before this piece of code is evaluated, it takes it, it checks what the first member of the form is. If it's a plus, it attaches minus to the rest of the form. If it's a minus, it attaches plus to the rest of the form. And if neither is true, it just returns the form. So this is a very simple example of macro-based metaprogramming, but there are much greater depths we can get into. And we'll see some of that as we explore April. So for now, let's see how April itself works. Right now, my REPL has me inside the April package. You can think of a package as somewhat analogous to a workspace in APL. It's like a symbol table, or you could consider it more like a namespace, since it doesn't represent the entire contents of the Lisp instance's memory. So being inside the April package, I can simply call April. And doing this, I get this back. So this is how Lisp represents a vector, this # 234. Let's try something two-dimensional. And this is how Lisp represents a matrix. And if I add a -f onto the end of the April invocation, I can display the APL style printout as well. So while the Common Lisp format obviously is more cumbersome than the APL representation, but the Common Lisp representation can actually be dropped into code and used there. So that gives me the total size of this array. So the APL notation obviously can't be used for that. So this is one of the things I like about using Lisp, is that I can have inline matrices and higher rank arrays. When you want to do inline higher rank stuff with APL, you're basically stuck doing lots of comma gets type stuff. So having looked at this, you can think of Emacs, the Emacs mode that I'm using, as being similar in a way to Dialog's ride. So, and then to continue the analogy, most of the common Lisps and other Lisps have a command line mode, but people don't tend to use them in that mode. They use Emacs or other environments as wrappers around those modes because of the added amenities that they offer, just like ride. And they, like ride, they contain interactive debugging features, stack traces, things of that nature. And then back to this usable in code, Lisp is a homoiconic language, so everything that it outputs is a form of data. Code and data are the same in Common Lisp in a way that they aren't in other systems. So that being said, let's explore one of the April demo applications. I'll be switching to that in just a moment. So in a moment, you may be able to better tell what this is. This is a terminal application displaying Conway's Game of Life, but the cells aren't displayed directly. Instead, I use a convolution kernel to draw lines around the cells. These box drawing characters surround the cells, and then the background color of these characters represents the presence of cells over time. So this is a square with cells that have existed in all the last 5 turns. That's why they're all lightly colored. And then these are all traces of cells that existed either at some point, either in the present or in the past. So for instance, being outside the outlines, these cells are now dead, but they existed in the past. So you see sort of a ghostly progression of cells as the generations go on. You can see down here, there's a textual explanation. Hit R to restart. And now let's take a look at the code for this. So here within Emacs is the April demo, the ncurses demo. And at the top, so this will give you a simple example of the APL Lisp integration. At the top here is the APL, is the main APL part of this program. So here we've got Conway's Game of Life. We've got a function to fill up a random matrix that produced the weird rectangles you saw at the beginning. And then this trace function is what's used to draw those outlines. It uses the stencil operator here to implement a convolution kernel, which it ravels each 3x3 matrix and then decodes it as a binary number. And those numbers are used to generate the box drawing characters that you saw there. And then this longest piece of code here is used to create the lookup table for the binary decodings and the box drawing characters. So this would take much, much more code to write if I were to do this in Common Lisp. Now down here, I have some kind of convenience functions in Common Lisp, and then the render function, which wraps another block of APL. So I can either initialize the matrix if there's a new state, or I can either produce the next generation. Then I can add the latest iteration to the history, which is reflected in those background colors, like I said. Or I can use this trace function. That's the core of this. That's what draws those lines. Then after this is done, I assign I basically iterate through the array and assign each element to the matrices that get shown on the screen. And then this is using a Common Lisp library called Croatoan, which provides access to ncurses. And this provides that basic keyboard input logic, the R, G, and Q key controls. So this is one example of the fusion of Common Lisp and APL. So having said that, let's explore some aspects of April's design. What we're looking at now is April's spec.lisp file. And this is the core of, really the core of April. So it starts, after this part, it starts with almost most of this file is the invocation of a giant macro. I showed you a very simple macro. This is a much more complex one. This macro is called specify_vex idiom. The idiom I'm specifying is called April. Then we have some basic system configuration. These profiles control, basically they arrange sets of unit tests. These are utility functions. For example, this matches the numeric character. This matches a character that can be part of a variable or function name. And this is the function that strips out the comments. Notice that it looks for the lamp character. And then after the utility functions, we get to the real meat of this. Oh, and here are all the quad variables, constants, and functions that are available in April. And after that, we get to the real meat, which is the function and operator specifications. So April uses a core specification to define all of its language features. This has allowed me to iterate considerably faster than I could have done with another approach. For example, here's the addition function. So for instance, it has the properties, its identity is 0. So that means that adding up an empty vector gets you 0, whereas multiplication has identity of 1. And they contain things like the inverse forms of these functions for different arrangements when used with the negative power operator. And also things like this scan alternating behavior. So as a lot of you probably know, the scan operator can be optimized for use with a non-commutative function by minus or divided by taking that function, applying it to every other element, and then taking the inverse form of that function, like addition in the case of subtraction, and then scanning it by that function. So that bit here is picked up by the scan operator implementation, which we can find here. So if the scan alternating is found, then it implements it in this way, which is much faster than the naive implementation of scan. So this spec contains a lot of information that is used for these functions, and it also contains their unit tests. So the spec also kind of documents what the function does when you pay attention to these tests and what they output. So here are our scalar functions. Here are our logical functions. These are, now we're getting into the array functions, iota, row. The catenate needs a lot of unit testing, likewise with take and drop and all their special cases. The rotation functions, encode and decode, and then after those we get into, after the evaluate and assign, kind of the more arbitrary things, we get into the operators. So they each have tests as well. Stencil needed a lot of testing. And then another unique thing about April is that there have been different approaches to adding on some more logical functionality to APL. Dialog's approach and the approach of some others has been the control statement system, where you write the things like the if colon, else colon. So this, I didn't want to approach something like this for April. I decided to bring in some elements from other languages, in this case, K, to implement, to express those things in a more succinct way. So this is the K-style if statement found in April, and I consider it to be a lexical statement. So you have lexical functions, lexical operators, and with this you have lexical statements. So a guard obviously can do some of the same things, and April supports guards, but what guards cannot do is have multiple statements within any clause of this expression. So it's more akin to the ifs, to the if control statements. You can do pretty much whatever you want inside there. And later on, we'll see a more expansive example of that. There was also an example in the end curses demo. But the neat thing that Lisp allows me to do is I can express a spec like this in a format that it looks kind of like a markup. This kind of structure you could also do in XML. But unlike XML, this is actually something that transforms into working code. And this spec-based organization has allowed me to iterate much more easily than I otherwise could have. Another interesting feature for us to check out will be the pattern matching system. APL is known for its special code, like the other vector languages. They can recognize patterns that can be interpreted more quickly than they would be if you just did the naive interpretation. And April has the same feature. So it will look for common expressions and optimize them. So this, for instance, optimizes the sum until pattern. More of a benchmark than a real useful case, but this tells you, this shows you how this is optimized. Something that's more useful is something like disclose, rotate, ravel. If you interpret that literally, then you're raveling an array, you're rotating the entire thing just so you can get the first element of that rotated array, when what you really want is simply the last row major element of the array. So that's what I do. I just get the last row major element of that array when I encounter this. Another example is rank, of course, getting the unique raveled elements. So obviously much work has to be done here in order to reach the level of special code that the established vector implementations have. But this gives me a robust framework to pursue that goal within. And then another interesting feature of April is that the compiler is designed for transparency. For instance, April uses what you could call a 2.5 pass compiler. The characters are first fed to a lexer, which produces this lexer output. You see here that the order of these is reversed, and that the plus character has become this function, this list of a function symbol and the plus character. The way you express a single character in Lisp is like this, with the hash \. So note that this has been turned backwards. That's because obviously APL reads from right to left. So reversing it is intuitive when you're feeding it into the compiler. And because Lisp uses linked lists, which are a last and first out, then that it's just makes sense from both sides of that equation. Then to see what the compiler produces, I can pass the compile only option, and instead of actually evaluating this compiled code, it will simply print it. So this is a macro. So if you don't specify a workspace for your evaluation, it'll place it in the common workspace. Let's see what that does. So when I macro expand this, all of these variables are interned in the common workspace. These workspaces are implemented under the hood as Common Lisp packages. So macro expanding that basically assigns them to their actual place. But a lot of work has been done to make this compiled output relatively human readable. So if you want to understand how this code works, you can view it at any time. And from this point, let's take a look at one of the most dramatic recent April applications. Actually, for the moment, let me stop the share, and I'm going to send you the first 2 lines of the APL file here. So those of you in chat, can see these 2. So perhaps somebody out there could guess what kind of program I am starting with this variable assignment. Can anybody guess what these pieces are fitting into? That's correct, Adam. This is code for what I'll call a falling block game. So let's share another.
Is it possible to show on your screen the bits of code that you'd previously pasted into the chat?
Yes.
Just for the sake
We'll look at that in a moment. But one of the latest Bloxl applications has been this falling block puzzle game. So this was implemented using April and Common Lisp. Here we can see the basic gameplay. And now let's jump into the code. So if everyone can see the Emacs here, this is the Lisp file that begins. So here we have the 7 pieces, the dimensions of the visible play field, the number of pieces that are to be queued in memory, and the rest of this game definition is largely data driven. So for instance, I look at the dimensions of the pieces. Let's format that nicely. So in order to implement this game, you need a solid barrier around the play field. Let's look at the play field here. So you need a solid barrier around the play field that is large enough so that when you push one of the pieces up against it, it will not overlap before one of its solid bits interferes with the solid material here. So what I do is I look for the largest 2x2 matrix inside one of the pieces. And the pieces are all designed as matrices like this because in order for them to rotate properly, this is how they're implemented. So you take this matrix for each of the pieces and rotate it in order to get the standard rotation behavior that you expect from the falling blocks. So what I do here, for instance, is I use the power operator until searching for a n by n matrix of zeros inside each of the pieces. I add 1 to the value each time until I found the largest n by n matrix that I can. And the rest of this is similarly data driven. Then we have the insert. We place a field on the play field, and then the clears function, which checks whether a piece's position is clear of other material. And then here in the action function, these are the 4 basic actions that constitute the game. So placing an item on the field, shifting it left or right, turning it, and then advancing it downward. If a placement fails to clear, that means the board is filled, and that's the lose condition. If there's a failure in advancement, if there's no clear there, then it is the piece is added. So here you see some of these case-style if statements being used in a larger format. So having seen the APL code, let's take a look at what I did in Common Lisp. For instance, this is basically the piece that forms the connection to the Bloxl display. See, I have the width and height of the display specified. The height is -20 because it is flipped in the vertical direction. You can make these values negative to flip them. And then this is the host address. And then this is the basic function that draws a pattern on the display. And then down here we have the main game loop, which it displays random color patterns until somebody presses a button on the controller. And then this is the main play function. So here we have those shift and turn actions, the place. So this is the interface for those functions within the APL code that you were looking at. So what I like to do with Common Lisp is semantic things like this. You see how I have these symbolic parameters here? This is the kind of parameterization where Common Lisp excels, whereas when I use APL, I want to do the hardcore, crunchy array mechanics. And then, for example, these flicker frame factors are used to, I have 4 different algorithms to flicker the pieces when a line is achieved. And then this is the display score, which happens at the ending. And then some of this is new, but you'll discover the reason for that later. But for now, let's just watch the video. And if any of you have questions, let's go ahead. Let me check the chat for questions, since not everyone may be on mic. Can you guys still hear me? Okay, so Aaron, do you see the APL code is designed to fit within the larger code organization of a Lisp source, or do you plan to add significant architecture or module level features within the April compiler? So are you saying like, for a given application, would I create a custom variation of APL code within it? And you see that in the video, that's the line effect. So each of those was custom coded, as you just saw. I see. So yes, you have namespace. So April implements namespaces like other APLs have. Aprils are implemented a bit differently because they're software packages. So you, in a given application, you'll generally create a namespace for it, like I did for this Bloxl game, and you will you'll place your functions inside there. And then the other thing about April is that April is customizable for different use cases. So to show that for a moment. Another question, is the April runtime written entirely in Common Lisp? Yes, it is. It contains some APL, obviously, for running its for its library set, but all of the implementation is in Common Lisp. So if everyone can see the share here, down at the bottom of the spec file is an example of a form called extend vex idiom. So this actually extends the compiler with a new function called add3. It's a rather silly function. It just adds 3 to its argument or to the sum of its arguments. But this shows you how simple it is to add on. This is one of the features afforded to me by Lisp, is that this extend vex idiom is a variation of the giant macro here, which is specify vex idiom. So it acts as basically a patch or extension on that idiom. So if you have a set of lexical functions you wish to use in your application, you can add one of these extensions or patches. You can make it a separate Common Lisp package, depend on it, and then that will be your, that can be part of your local APL setup. And then you said, do you use the K-style vector of vector representation? You use a full flat representation for flat arrays. Yeah, I use a flat representation. One of the advantages of Common Lisp is that, as I showed before, it has native multidimensional arrays. So this here is a two-dimensional array. Let's inspect it, something we can do in Common Lisp. See dimensions 2 and 3, total size 6. One of the things that makes Common Lisp such a good language for implementing an APL is that it has almost all of the features that you need built in. It even has zero rank arrays. Let's enclose this. That hash zero array, that's a zero rank array. The only array feature that Common Lisp lacks, which APL has, is empty array prototypes. So if you have an array of arrays and then you reduce its size to 0, then you can lose the ability to add those arrays. Then if you want to expand that, then you wouldn't have that prototype available to you. But I made this work via a hack. I used a feature called array displacement within Common Lisp. When an empty array is created by a function like shape or drop, I will displace, I will put its prototype, if there was an array prototype, into this special prototype object that's displaced to the array. And yeah, Adam said, yeah, CL does have native n-dimensional arrays. Actually, the current builds of SBCL can go up to 255 dimensions. Older builds could get as high as, I recall, it was 2 to the 16th power minus 7, but that's been disabled in the more recent builds. I think it was causing them some speed issues. So I might have time for one more question. Time is running down here. Anything else? So thanks to everyone for joining me today. And one more thing, I'm going to have a little room in the meetup after the main APL seeds is concluded, and I will be providing an interface that you can use to actually play the Bloxl Tetris. So there's going to be a live camera feed of the Bloxl, and then there's going to be a control panel, and I can give people one by one access to my screen to click on the buttons and play it. So if anybody would like to try that out, I'll be hosting that in my room following the event.